This is Online JAB Class Academy. I'm your chemistry teacher, Christopher Gonzel. Now today we'll be looking on the topic factors affecting the rates of a reaction. At the end of today's lesson, a student should be able to do 1. Identify the factors that affect the rate of a chemical reaction, and 2. Explain how temperature, concentration, surface area, and the presence of a catalyst may affect the rate of a chemical reaction. Now, when we talk about factors affecting the rate of a reaction, we're in essence talking about things that changes in their level may either cause an increase or a decrease in the rate of a chemical reaction. Some of those factors include temperature at which the reaction is occurring, the concentration of the reacting particles, the presence of a catalyst, and the surface area of the reacting particles. Now let's start by looking at the effect of temperature on the rate of a reaction. Now, if temperature increases during the course of a reaction, what you'll find happening is that as the temperature goes up, the particles, the reactant particles, will have greater energy. They will be moving a lot faster. And so what those two changes will result in is greater collision amongst the reactant particles. And as the reactant particles collide more frequently because they're moving faster, and as they collide with greater energy, the possibility of bonds within the reactants being broken is actually increased, and that will lead to greater formation of products, or the formation of products in shorter time. And so that will cause an increase within the reaction rate. And that is opposed to a situation whereby temperature is much lower. If the temperature is lower, what will happen is that the reactant particles won't have so much energy, and so they'll be moving a lot slower, and as a result of that, collision will be infrequent. In addition to that too, because the particles don't have enough energy, the possibility of their colliding and actually breaking bonds within the reactants is actually reduced. And so the formation of products tend to be a lot slower. And so, in short, an increase in temperature will result in an increase in the rate of a chemical reaction, whilst a decrease in temperature will lead to a decrease in the rate of a chemical reaction. A graph wherein the rate of reaction is plotted against temperature will of course then show that as temperature goes up, the rate of reaction actually increases, and so the graph will have this general shape. Now let's turn our attention in looking at the effect of concentration on the rate of a chemical reaction. But just before we get into it, let's look at what concentration is. Concentration really is a measure of the amount of a substance that is found within a fixed volume. And so if the amount of a substance in a fixed volume is low, then the concentration is defined as being low. If the amount of a substance in a fixed volume is high, then the concentration therefore is regarded as high. And so in box 1, where we have a low number of reactant particles in a set volume, box 1 therefore has a low concentration of such particles. In box 2, that has a large number of reactant particles in that same set volume, box 2 is therefore said to have a higher concentration than box 1. Now, what implication does this have for the rate of a reaction? If the concentration is high, and by that we mean we have a large number of reactant particles within a set volume, the particles, because they're greater in number, they will be colliding more frequently with each other. And with greater frequency of collision, what will happen is the possibility of bonds being broken within the reactants will be increased, and the formation of products will also take place a lot faster, and as a result of that, the rate of reaction is increased. Now, if the concentration is lower, and by that we mean you have a low number of reactant particles within a set volume, the frequency that they will be colliding with will not be great, as the reactant particles are much further away from each other. They are not as crowded as we saw over here, and so they won't be colliding a lot frequently, and as a result of that, the possibility of bonds being broken within the reactants is much lower, and so the formation of products is much lower, and as a result of that, the reaction rate is much lower in the case of a low concentration of particles. And so in short, as the concentration of reactant particles increase, the rate of a chemical reaction will increase, as the reaction will be occurring much faster. On the other hand, if the concentration of reactant particles decrease, the rate of chemical reaction will indeed decrease. Therefore, if a graph of rate of reaction is plotted against the concentration of a reactant particle, the graph will have this general shape, showing of course that as the concentration goes up, the rate of the reaction increases. Let's now turn our attention to surface area and the effect that surface area has on the rate of a reaction. It's important in pointing out in starting that reaction of solids take place at the surface of the solids, and so the greater the amount of the surface of a solid which is exposed for collision, the greater will be the rate of reaction. If we take this large cube, which is made up of 8 smaller cubes fused together to give you the larger version, not a lot of the surface of the cube is exposed. What we are seeing here is that the outer surfaces of its parts are exposed. However, the inner parts which are fused are not exposed. And so what will happen during the course of the chemical reaction is that the green reactant particles will be colliding with the component parts of this large cube. However, the collision to the surface is going to be quite limited, as it's only the outer parts that the green reactants will be able to interact with, and that will result in the reaction rate being a lot slower. If, however, this large cube is broken down or broken up into its smaller parts, more of the surfaces of the smaller parts are now exposed, and so what can happen is that the green reactant particles can now interact with more of the surfaces of the component parts, and as a result of that, the reaction rate is going to be much greater, and it's much greater because greater surface is exposed, and therefore the green reactant particles can collide with more of such surfaces. And so important in noting is that the smaller particles are, the more of their surfaces that are exposed, and therefore the greater is their surface area, and as a result of that, the faster is their rate of reaction. As opposed to the larger the particle is large, the rate of reaction is going to be lower, as the larger particle has a lower surface area. Therefore, if we place 2 grams of marble chips into a test tube and we collect another 2 grams, but this time we grind it into marble powder and we place that in a second test tube. And if we now add 10 centimeter cubes of hydrochloric acid to each, to the marble powder and 10 centimeter cube to the marble chips, what you will find is that the rate of reaction between the hydrochloric acid and the marble chips is going to be low. And why is it low? Because the surfaces of the parts of the marble chips are not fully exposed to the hydrochloric acid for reaction, and so the reaction will proceed slowly. And that is opposed to what we'll find over in test tube 2, when the hydrochloric acid is added to the marble powder, because the marble powder really is the component parts of the marble chips being separated, so to speak. What you have is a fuller exposure of the surfaces over here with the marble powder to the hydrochloric acid, and as a result of that, the rate of reaction can proceed a lot faster. And so over in test tube 2, what we have is greater surface area, because the reactant here is in a powdery form, a smaller form, and so the rate of reaction is actually faster, as opposed to test tube 1, where the reactant is much larger and therefore has a smaller surface area exposed. Over here, the rate of reaction, of course, is much lower. Let's now look at the effect of catalyst on the rate of a chemical reaction. By definition, catalysts are chemicals that change the rate of a reaction without being permanently changing the process. Now, how do they work? Catalysts work by actually providing a different way for reactant particles to interact. Now, this alternative way that the catalysts enable has a lower activation energy, and as a result of that, it means that the reactant particles do not have to collide with as higher energy as before in order for them to react. And as such, because the particles can now collide with a lower amount of energy, a lower activation energy, more of the reactant particles will possess this lower energy in order for a reaction to take place. And so what you'll find is more collision will be resulting in the formation of more products, and so the reaction rate actually increases. For example, when hydrogen peroxide breaks down, whenever it decomposes, water and oxygen gas are formed. It is observed that when manganese oxide is added to the process, the breakdown happens a lot faster. Now, what has happened here is that the manganese oxide is acting as a catalyst, and what it is doing, it is providing an alternative way for the hydrogen peroxide molecules to react in order to form water and oxygen. And that new pathway that manganese oxide is providing, it is associated, it has a lower activation energy. And because it has a low activation energy, what happens is that the hydrogen peroxide molecules can now collide with each other at a lower energy and be converted into products. And that, in essence, that in short, is what explains the faster rate of breakdown of hydrogen peroxide in the presence of manganese oxide. Now that concludes our lesson today. Hope you enjoyed. Thank you.